Good morning to all.
Good morning, sir.
Let us have a look at the revision of our what we have done. But before that, we will also have a look at the syllabus of your course. I mean, we want to know where we are and what is the time limit that we have. So I'm sharing the screen now. If you have any comment to make, you can make.
No, sir.
Okay. I'll share the syllabus now. Can you see it?
Yes, sir.
This is the syllabus. So the first thing is non-linear spaces, Banach spaces, classical examples. We have done all these things. LP, C, C0, C01, LP01. Continuity and boundedness of linear operators we have done. Quotient spaces, I have done it. Not in detail. Finite dimension non-linear spaces, I quickly gave the thing. Rees lemma. Rees lemma is part of the finite dimension non-linear spaces. Non-compactness of the unit ball, that also I have done. Separability with examples. That I have to do. Okay. Let me look at the second part. Hahn-Banach theorem extension. Then we have to do open mapping theorem, closed graph theorem, uniform boundedness principle. As soon as this is over, we'll start with Hilbert spaces. Okay. So today, this week, I want to finish at least one theorem. So uniform boundedness principle. Okay. Hahn-Banach theorem and other things, we have done it. We have done something little more. We have also done weak and weak convergence and weak star convergence. Dual also we have done it. Double dual also we have done it. Okay. In your syllabus, I don't see reflexivity anywhere. So let us remove it from the matter. Okay. All right. So for uniform boundedness principle, I need 2 lectures. Open mapping theorem 2, closed graph theorem 1 lecture. 5 lectures for this. And the remaining lectures will be on Hilbert spaces. Okay. That is the story. So let us start revising. Okay. What is that we need for proving the open mapping theorem or something? It is the base category theorem. Okay. For base category theorem, you should know what is an interior, what is a closure, what is nowhere dense set, and what is a dense set. I will revise this part and then start with the lectures on, So the standard thing is that we do it in a metric space. So this XD that we have is a metric space. We have some standard thing. B x0 or 1 is nothing but the ball of radius, okay, dxy less than 1. Sometimes we write this as also b1x. I mean, it depends on what you want to write. bx1 or r with the bar on the top, red as closure of closed bxr is nothing but set of all y such that dxy is less than or equal to r. So first thing, take a set A in X X is called, I've done this interior point. If there exists a ball of radius r positive such that the ball of radius r is contained in A. A interior, A with a 0, you read this as interior of A. This is also written as INTA. This is nothing but set of all y such that y belongs to A is an interior point. Okay. So example, let's take x to be r, dxy to be mod x minus y. Let's take q to be rationals. What is the interior of q?
Um,
Pardon?
Sir, all the points that are not on the boundary and inside the ball are called interior points,
But
sir.
q has no boundary, no? It's an unbounded set.
The open set, sir, is the interior, sir.
What is the interior? Give me the. Is this done or not in your metric space? See, take x.
Done, sir.
Huh? Suppose
It has been done.
R is a rational. Let me take a ball of radius k. Does it contain irrationals? Answer quickly. Does it have irrational or not?
So if we take rational numbers, then we we can't draw balls, sir. If we take only rational numbers, sir.
Why you can't draw the balls?
In
Huh?
on
Well,
real
you can
life,
draw the balls. What's the problem?
but
What it has to do with you? That's what I'm asking.
it contains irrational also, sir.
So BRK is not contained in A,
Yes, sir.
right?
Yes,
Therefore,
sir.
interior of Q is, there is no interior point. So what
Yes,
is
sir.
interior?
Phi, phi.
Very, very good. So it's empty set. Same thing. Interior of the irrational is also empty. Okay?
Yes, sir. Yes, sir. Okay.
Okay. Now let us look at the closure. So closure of A is A union its limit points. This is denoted by CL of A. It's also denoted by A with a bar on the top. Okay. Now, if you look at the ball of radius R around, say, some point X, and if you look at the closure, this is actually equal to set of all y such that distance of x comma y is less than or equal to r. In our notation, we had written it as brx with a bar. So these two notations match. Okay. Let's take an example.
Okay, sir.
Look at IR to be irrationals of the metric space X. What is the closure of IR? Quickly answer it. Closure of IR. Pragna.
Sir, R,
Very good. What is the interior of IR?
it's phi, sir.
Same argument, right? Fine.
Yes.
Now, a set B in a metric space XD is called dense. Dense in X, okay? If closure of B, that is B closure, is X. Okay? You know this definition or not? All right.
Yes, sir.
Nowhere dense set. A set A in a metric space XD is called nowhere dense. It is also called a rare set. If the interior of the closure is empty. It's not a thick set. Okay, example.
Sir, what is thick set? I don't
It's
know.
also called. Thick means it contains an open bulb.
Okay, sir.
Okay. Let's take example. Let's take R2. You take a line. Does it contain a ball?
No, sir.
What is the area of this line?
Line, sir, there is no area, sir.
Area is 0. Don't say
Yes,
no area.
sir. Yes, sir. Area is 0. Yes, sir.
So normally we call a set as a thick set if the area is positive. This area is 0. Therefore, it's called a thin set. It cannot contain an open ball. Okay. Example. Let's take rationals in R with the usual metric. Okay. Is it dense? What is Q closure?
R, sir.
Very good. Therefore, Q is dense in R. Similarly, irrationals is dense in R. Let us take integers. Huh? Let's take integers. Okay. What is the interior of integers?
There is also phi.
Hmm?
Interior of integers is, sir, phi, sir.
Empty set.
Yes.
Okay. What is the closure of this Z?
R, sir.
Integers. Huh? Method.
Integers. Then integer.
Right?
Yes, sir.
Okay. Now you look at the interior of Z bar. That is nothing but interior of Z. That is equal to empty.
5. Yes, sir.
Therefore, Z is nowhere dense. Okay? Okay? Okay.
Yes, sir.
If you know all these things, I won't do it, huh? Or you
Sir,
want a quick revision?
sir, we know closure, interior, and dense.
Shall I move to the lectures, main lecture?
Just a quick revision, sir, if possible. Because we have studied in third semester, maybe forget some definitions, sir. Yeah,
No, the
confusion.
question is that you want or you don't want. That's it.
Sir, we want, sir.
Okay. Let me give you one or two more examples because that will be essential. What it says is that you take x equal to C01 with L infinity norm. What does it mean? Supremum norm. Okay. Take the polynomials in X. Is it dense?
Yes, sir, because we take a continuous function, then all polynomial is continuous.
By Weierstrass theorem.
Yes, sir.
Okay. A metric space XD is called separable if there is a set A contained in X, A countable and dense. Okay? All right.
Sir, what is the meaning of matrix is separable, sir?
Hmm?
So what is the meaning of a matrix is separable? So we understand by definition, sir. Like, can we understand, sir, by some geometrical yeah, example, sir? Then
Matrix. There is no matrix, no?
you said na let X be the called metric space.
No.
Metric
Metric space, yeah.
metric space. Sir. I'm saying metric space.
Yeah.
What is the meaning of separable metric space, sir?
That is, there exists a countable dense set.
Okay, sir. Is there example, sir?
Mhm. Take X equal to R. Okay, this is separable because Q is countable, rationals are countable, and Q closure is R. Clear?
Yes, sir. Yes, sir.
This is a countable dense set. Does it help it? Does this help you?
Yes, sir. Thank you, sir.
Okay. Second example. Let's take Rn with the usual metric. Okay. Is it separable? Hmm? Separable or not? It is separable. Okay. In general, okay, in general, let x1, x2, xn be separable spaces. Are the same scalars. Then the product x equal to x1 cross x2 cross x3 is separable. Okay. What you do is, this is separable. So you take a dense subset K1, take a dense subset in X2 which is separable. Then you look at K1 cross K2 cross Kn. This set K will be a dense separable set, a dense countable set. This proof is simple. Okay, I will not do it. Huh? Third example, LPR. LP spaces, sequence spaces. 1 less than or equal to P less than infinity are separable Banach spaces. Proof I will omit. Omitted as of now. Fourth example, L infinity R is not separable. Okay. Same way, capital LP also. I will not do that. Okay. I will stop this point at this time. And move to can you see the book?
No, sir.
No?
No,
No,
sir.
sir.
I'll share it. Huh? Can you see it?
Yes, sir.
Sir.
Okay. This was the thing which I wanted to tell you. Theorem, 1 less than or equal to P less than infinity metric space LP is separable, but L infinity not. So for this, what you do is you take for 1 less than or equal to P less than infinity, take the standard Schauder basis, EJ, 1 at the jth place and 0. And you look at the set E equal to K1 E1 plus K2 En plus Kn En, n equal to 1, 2, etc. And you take this as real. Okay, he is doing it for complex. Take all the K1, K2, Kn as rationals. Then this is the union of countable sets, countable union of countable sets, and therefore this E is countable. And you can show that this set E is dense. The proof is given here. Okay, not a difficult proof. Okay, I will not do that. I will send this material to you. Okay. On the other hand, L infinity is not separable. Now, how do you show that? You give the proof, you know, by contradiction. All right. Before that, you look at a set S. x in L infinity such that xj is either 0 or 1 for j equal to 1 to n. Please note this is a L infinity space. Therefore, all elements can be 1 also, or all elements can be 0 also. Only thing is the elements are either 0, elements of the sequence are either 0 or 1. Now, when you look at this d infinity, the L infinity norm of x comma y, for all x not equal to y, okay, is 1. Okay. Assume that x and y are not 0. Is this clear or not? Huh? The distance between 2 points is going to be 1 because the distance is, you take xn minus xj minus yj mod of that and take the suprema. So since x and y are not 0, at least one of them will not be 0. So this will be actually 1 for all x not equal to y in S. Now
Yes, sir.
let x1, x2, xn be a countable subset of L infinity. So we want to show that this countable set is not dense. What do you mean by countable set is not dense? If you take a ball of radius, whatever the radius is, there is one point which is not in this set, okay, or a multiple of that. So let us look at x1, x2, xn to be a countable dense set. Then 0 less than, choose r to be less than half but positive. Then u, x and r contains at most 1 point. If it contains 2 points, then the distance is 1. Okay. So obviously, the fact is that the distance has to be 1 here. So if it contains 2 points, the distance between those 2 points will be 1. But we are taking a ball of radius half. So it can contain at least only 1 point from S. All right. But since S is uncountable, this set S is uncountable. Why is it uncountable? Why S is uncountable? You can take an irrational and look at the binary form of that. Okay, that will have this sort of either it is 0 or 1 for j equal to 1. Is it clear to you? An irrational, if you look at the binary representation of an irrational, it has infinite number of elements, non-zero, because it's irrational. If it is finite number, then it will be a rational set. Okay. If you have a number in the real line, if it terminates, if it has a terminating decimal, then it is rational. So an irrational cannot have a terminating decimal. Therefore, it will have infinitely many elements. So either 0 or 1, it will occur almost everywhere. So this S has, X has, S has an irrational. So all irrational elements will go into it actually. So S is uncountable because of irrationals are uncountable. So there is some X in S such that X is not in UR. Why? Because UXN can contain at most a countable number, but it has uncountable number of irrationals. Therefore, it cannot contain. So there is an X in S which is not in this one, which means that the intersection of x1, x2, xn, intersection ux0 is empty. So that x1, x2, xn cannot be dense. That is the simplest proof that L infinity cannot be dense. Okay. From where did you get this part? This part is a consequence of this result. Okay. A subset, if X is separable metric space and Y is contained in X, then Y is a separable induced matrix. Okay, this also. Otherwise, we can construct. Let me see what he gives. Okay. So that shows that L infinity is not separable. All right. completeness we have done it, okay? Every Cauchy sequence converges in it. We have done this theorem also, that 1 less than or equal to p less than infinity, in fact include infinity, that LP is complete, okay? This we have done it in the class. This is the Bayes theorem. Have you done Bayes theorem? Let X be a metric space. Then the intersection of finite number of dense open set is dense. So if you take a metric space, the intersection of finite number of dense subsets is also dense. That's an easy thing to prove. If X is complete, then the intersection of countable number of dense set is also dense. That is the advantage of completeness. It has to be, it gives you more leverage, to work with. So if X is a complete metric space, then the intersection of countable number of dense sets is also dense. This is what is called the Bayes theorem. This was done in 1899. Okay. I will not go into the proof because it's not part of your syllabus, but this is part of the syllabus of your metric spaces. If it has been done there, it's good. Otherwise, chalega. Okay. So this is the Bayes theorem. If you want, I will send the proof. It's a very beautiful proof given in the book of Limaye. All right. Now let me come to the main aspects. This is the uniform boundedness principle. Okay. This is what is called the uniform boundedness principle. Let X be a Banach space and Y be a non-linear space. So you have two spaces here. One is a Banach space, X is a Banach space. What do you mean by Banach? It's a complete non-linear space. Let Y be a norm space, it need not be complete. Okay. Now this script F is a subset of BLXY such that for each X in X, so if you take any X in X, then F of X such that F is in F is bounded in Y. Okay. So this F is a subset of BLXY. Okay. What it says is, do you understand this or shall I explain? You understand this statement? F is a subset of bounded linear operators from X to Y such that for each X, the set F of X, F belonging to F, is a bounded set. Then for each bounded subset E of X, F of X, X belonging to E and F belonging to F is bounded. That is, F is uniformly bounded. Okay. Do you understand the statement of the theorem?
Yes, sir.
You understand this? This F, script F is a set of all linear operators from X to Y. Need not be
Yes,
countable,
sir.
need not be, it can be uncountable also. A very interesting application of this theorem is that there exists a continuous function whose Fourier series does not converge anywhere. Let me explain to you, okay? Otherwise, you might mistake it. Huh? You see, if you take L2, 0 to pi, then 1 cos x, etc., etc., and then sin x. Somebody would have done it to you. Sin nx. This set, okay, is a basis, Hamel basis.
Sir,
Excuse me, sir.
Yep. Tell me.
Sir, your screen is not visible, sir.
Just hold on. I'm sharing it now. Yeah. Is it visible?
yes, sir.
Okay. It's a Hamel basis. It's actually not a Hamel basis. It's a Schauder basis. What X? What do you mean by this? That is, if you take any f in X, it has a Fourier series. An cos nx plus bn sin nx. Let me call this as S of x. Okay. Then this, if you look at the partial sum Snx minus f in L2 Naram will go to 0 as n tends to infinity. So this is in L2, okay? And what is the relation between this f and x? So normally we write this as not f equal to, but f something similar to Sx. This is called the Fourier series. Of f. So if f is a discontinuous function, okay, suppose you take f to be something like this, say 0 up to pi, and from pi to 2 pi you take it as 1. Then what is the value of f of pi? Let me not say value of f of pi. What is the value of s of pi? Yeah, it's the average value, right? Average of the left and right. Yes or no?
Yes, sir. Yes, 1 by 2.
You remember this, right? So this is not equal to fx, huh?
Yes, sir.
Either it is 0 or 1. So that is why you don't write equality here. Now you have two things. This is a function of x, so you can talk of pointwise convergence. What uniform boundedness principle says is that there exists a function f for which Fourier series does not converge pointwise. Anywhere, pointwise convergence is not possible for the Fourier series. That is the application of the uniform boundedness principle. I will try to do it, but you should know Dirichlet theorem for that. Okay. So what it says is that f is uniformly bounded on E. In particular, supremum of the norm f in f is actually bounded. So what we do is we define a set here, n equal to 1, 2, 3, define dn equal to x in x such that norm of fx is greater than n for some f in. So even if for one f in f, if norm of fx is greater than n, then you define this set to be x. Suppose there is no such x, then it's uniformly bounded by n anyway. So you don't have to worry anything more.
Sir,
Hmm.
the screen is not visible, sir.
Sorry. Sorry. Is it visible now?
No, sir.
No?
Yes, sir. Not visible.
But I have shared it. I'll again share it.
Yes, sir. Now it's
It says
visible.
stop set. Yeah. So the proof of this is that you take the set n equal to 1, 2, 3 such that dn is x in n such that norm of fx is greater than n for some f in n. Okay. Suppose you don't have any such set, then it's only for the supremum is almost finite because there is no such x. Let's assume that dn is not empty. For each f in f, the function f going to norm x is continuous. Why is it continuous? Because f is a bounded linear function, therefore it's continuous. Norm is a continuous function, therefore composition of two continuous function is continuous. Therefore f going to norm of fx is continuous. So that the set x going to x fx greater than n is open set. That's obvious. That's an open set. Since Dn is the union of these sets, obviously this Dn is nothing but union of such sets, then Dn is open in X. Okay. Arbitrary union of open set is open. Let X belong to X be fixed. Fix X. And by hypothesis, norm of Fx is less than or equal to n X for all F in F. For some positive integer n and X not in Dn. Okay. So if X is not in Dn, then norm of fx is less than or equal to n. Obviously, if it is not in Dn, norm of fx is not greater than n. Therefore, norm of fxn less than or equal to n for all f. It is for some f here, so it becomes for f. All right. That is x is not in Dn. Now, thus, intersection of n equal to 1 to infinity Dn is empty. You can't have, too many things. Anyway, that's a clear thing here. Okay. Consequently, intersection n equal to 1 to infinity Dn cannot be dense. Since intersection is empty, then the intersection of Dn cannot be dense. Why? If this is a consequence of the, anyway, intersection of Dn is empty and an empty set cannot be dense. It's obvious that empty set or a finite set cannot be just dense. Okay. All right. Anyway, what we need here is that empty set cannot be dense. Why empty set cannot be dense? If you look at the closure of an empty set, it is 0. Interior of the empty set is also empty. Therefore, it cannot be dense. Okay. So Bayes' theorem now implies that some Dn must not be dense. Why some Dn must not be dense? The reason is that if each Dn is dense, then the intersection of Dn is also dense by Bayes' category theorem. That was the reason why I was trying to, revise Bayes' category theorem. Okay, Bayes' category theorem says if X is a complete metric space, and if you have dense sets D1, D2, Dn, then the intersection of these sets is also dense. Okay. Completeness gives you countable intersection of dense set is dense. In this case, what is happening is the intersection itself is not dense. If the intersection is not dense, then at least one Dn has to be non-dense. Why? If all Dn's are dense, then this intersection would have been dense. But I know that it is not dense. Therefore, at least one Dn has to be non-dense. So call that as Dm. Okay, that's what. Is this argument clear or not?
Yes, sir.
If all Dn's are dense, then completeness gives you intersection as Dn is dense. But intersection Dn is not dense. Therefore, at least one set Dn is not dense. That's the negation of that. And so let's call that set dm as which is not dense. Okay, where is that? Yeah. Then there exists some a in x and r greater than 0 such that the ux ar intersection dm is empty. So if a set is dense, then it intersects with every a ball of radius r. But since it is not dense, then at least there is a point a for which the closure of the a ball of radius r around a point a, this is taken in x, is empty. That is y is in x and norm of y minus a is less than r, and therefore norm of fy is less than or equal to m. Okay, for all y in x. So this is the conclusion, because this point y is in x and norm of fy is less than or equal to m, because it has to be this point y is in x and in dm, and since it is y minus a is less than or equal to r, then it is in this intersection u bar xr intersection dm. Therefore, this y will go into dm also. Since it goes into dm, norm of fy is less than or equal to m. Okay. All right. Oh, sorry. It is not in dm. If it is in dn, then it has to be greater than n. So this uxr, this point y is in the u bar xr, and the intersection with dm is empty. Therefore, if y is in dm, I am saying if, then this will not be empty. This will be at least y. Since it is empty, therefore y cannot be in dm. What do you mean by y is not in dm? Y is in the complement of dm. Complement of this set dn is nothing but less than or equal to m. Therefore, norm of fy is less than or equal to m for all f in f. Okay, so that is the first conclusion of this part. Okay, the second conclusion is slightly important. I would like to do this in the next class because it is almost 58. Okay, it's almost 58 here. Okay, two comments. One comment is that I have sent one assignment to you for submission. I will send a second assignment today or tomorrow. Then you take one more week to submit it. But second assignment will have less number of problems. Okay.
Okay, sir. Do you have any quiz on Thursday in this week, sir?
That depends on you. If you are interested, I'll give. Otherwise, not.
Yes, sir. We are interested, sir, on Thursday, sir.
Which topic you want?
After midterm, sir.
No. Don't take such a long topic. Huh? Take something. Weak convergence and strong convergence.
Sir, Ridge lemma?
Hmm?
Ridge lemma? Yeah, what?
Problem is that Rees lemma, I have not proved it in the class. Then you will have difficulty. I said
Okay,
it's
okay.
homework for you.
Okay, sir. Then weak and strong convergence.
Take.
Okay.
Weak and strong convergence. All right.
Okay. Okay. Thank you,
I'll
sir.
set the paper today.
Yes,
Any
sir.
other comments? I'm
No, sir.
almost evaluating your paper. Almost it is done. There are some questions for which I might give full marks because of, or at least some grace marks. Question 6, I might give a grace mark, 5 marks or something like that. Okay, for everybody. So that nobody is, uh, nobody is, I might give grace 5 or 6 marks for the last question. Nobody has answered it. All right.
Okay, sir.
Anyway, in some sense, it is not in the, not that it has to do with reflexivity, but it's on functionals. Anyway, it doesn't look like it's part of, I have not done it in the class also. Okay. So for the last question, I'll give you almost 5 marks for almost all, free. And first question or second question, there is some issue. That L101, I gave there are 2 more questions where I'm going to give 4 marks, 8. So almost everybody will get about 14 marks almost free. 14 or 12. All right. So that's what I'm thinking. All right. Have a good day. Bye. Enjoy yourself.
Okay, sir. Thank you, sir.
Welcome.